and welcome to all people who are watching this online video. Before heading further to my speech on these online classes, I want to thank you all for your valuable presence. As you embark on this course, you are about to embark on a journey that will change your life. We designed the most informative and in-depth training we could to give you everything you need to succeed. This course will take time, but it delivers results. We are excited to be with you every step of the way through dialogue, engaging classes and assignments, and many more. Enjoy the learning process. Why we need to study hydrogeology in groundwater? Hydrogeology is the study of groundwater. It is sometimes referred to as hydrogeology or groundwater hydrology. Hydrogeology deals with how water gets into the ground, or in other words is known as recharge, and how it's flow in the subsurface through aquifer, and how groundwater interact with the surrounding soil and rock, which is the geology. More specifically, the hydrogeology component is intended to determine basic geological and hydrogeological conditions, including the geological description of existing soil and bedrock, the depth of the water table, and also the groundwater flow directions and hydraulic gradient. For this first online lecture, at the end of the lecture, you should be able to understand the significance of groundwater resources on Earth and also able to contrast groundwater and surface water resources. The Earth is a watery place, but just how much water exists on, in, and above our planet? About 71% of the Earth's surface is water covered, and the oceans hold about 96.5% of all Earth water. Water also exists in the air as a water vapor, in rivers and lakes, in ice caps, glaciers, in the ground as soil moisture, and in the aquifers, and even in you. The distribution of water on the Earth's surface is extremely uneven. Only 3% of water on the surface is fresh. The remaining resides in the ocean. Of fresh water, 69% resides in the glaciers, 30% underground, and less than 1% is located in lakes, rivers, and swamps. Look at another way. Only 1% of the water on the Earth's surface is usable by humans, and 99% of the usable quantity is situated underground. Groundwater is often hidden deep in the aquifers, permeable rocks, and sediment, and is extracted using pumping wells. Often, aquifer can be renewable water resources, slowly replenished by rainfall infiltration over hundreds up to many thousands of years. Population growth particularly will limit the amount of water available per person because an increase in per capita water consumption driven by the development will intensify water demand, straining the local water supply. In groundwater context, due to population growth, groundwater pollution has dramatically increased over the past 50 years as a result of intensive and extensive exploitation of these water resources for human consumption such as drinking and sanitation, and diverse economic uses such as tourism, landscaping, agriculture, energy production, and others. So how much of the world relies on groundwater? Underground aquifers supply 35% of the water used by humans worldwide. An estimated 20% of the world population depends on crops irrigated by groundwater. As can be expected, about 70% of the groundwater withdrawn globally, including in the US, is used for agriculture. In some arid countries, 90% of the groundwater used is for irrigation. Based on this worldwide groundwater usage figure, we can see that a back case of the probable trajectories of growth in groundwater use in selected countries is presented. In the USA, Spain, Mexico, and North African countries like Morocco and Tunisia, total groundwater use peaked during the 1980s. In the South Asia and the North China Plain, the upward trend began during the 1970s and is just plateauing now in 2014. A third wave of growth in groundwater irrigation is now taking place in many parts of sub-Saharan Africa and in some South and Southeast Asian countries such as Cambodia, India, Vietnam, Laos, Myanmar, and Sri Lanka. About 30% of the planet's available freshwater lie in underground reserve aquifers, basins, and other sources. Some of the world's most productive accessible groundwater supplies are shown in the map. Just as the distribution of lakes and rivers varies around the world, so too does the distribution of aquifers. Major basins, which is colored by purple, hold abundant, relatively easily extracted groundwater. More complex basins, which is colored by green, might contain multiple aquifers separated by impermeable rock or have layers of salt waters as well as fresh. Local and shallow aquifer provides only limited quantity of water. The long-term response of groundwater to climate forcing, largely independent of human activities, can be detected from paleohydrogeological evidence from regional aquifer systems in semi-arid and arid parts of the world. Much of the groundwater flowing in large sedimentary aquifers of the central United States, Australia, Southern Africa, and North Africa was recharged by precipitation thousands of years ago. As evaporation and plant transpiration consume soil moisture but leave chloride behind, substantial accumulation of chlorides in unsaturated soil profiles within these basins indicates that little or no recharge has since taken place. Natural replenishment of groundwater occurs from both diffuse rain-fed recharge and focused recharge via leakage from surface waters and is highly dependent on prevailing climate as well as on land cover and underlying geology. Climate and land cover largely determine precipitation and evapotranspiration, whereas the underlying soil and geology dictate whether water supplies can be transmitted and stored in the subsurface. This figure shows the mean annual groundwater recharge worldwide. Groundwater recharge, usually expressed as an average rate of inch of water per year similar to precipitation. Thus, the volume of recharge is the rate times the land area under consideration times the time period and is usually expressed as acre-feet per year. Recharge occurs when water seeps into the ground to replenish underground aquifer. Although some recharge happens incidentally, water flowing into the ground from rivers, unlined canals, or excess irrigation. Intentional recharge can restore groundwater level and store water for later use. So how long does groundwater take to recharge? When it comes to recharge, the individual basins vary greatly. The time it takes for surface infiltration to reach an aquifer as deep as 400 feet may take hours, days, or even years depending on the rate of recharge. Natural refilling of aquifers at depth is a slow process because groundwater moves slowly through the unsaturated zone and the aquifer. Groundwater abstraction is the process of taking water from the ground source, either temporarily or permanently. Most water is used for irrigation or treatment to produce drinking water. India was recorded as the largest user of groundwater in the world. It used as estimated 230 cubic kilometers of groundwater per year, over a quarter of the global total. More than 60% of irrigated agriculture and 85% of drinking water supplies are dependent on the groundwater. In some cases, if rates of extraction exceed rates of groundwater recharge within an aquifer, the water table can fall across a wide area. Taking too much water or over-extraction can lead to surface rivers dying or the level of groundwater aquifer and the water table reducing. This table shows the differences between groundwater and surface water resources from the aspect of hydrogeological characteristics and socio-economic factors. In terms of the quality, through runoff, air fallout, and other sources, surface water can contain significant amount of contaminants such as chemical pollutants. And because groundwater is connected to surface water system through soil percolation and seepage, it is also susceptible to contamination. However, the rock and sediment layers below the water table act as a natural filters. Therefore, groundwater generally contains fewer contaminants than surface water and requires less treatment.